Hello everybody, I hope all of you are doing well. So we'll be looking at a problem on rigid body vibrations today, and this is a problem that I have already drawn and kept ready for you. Okay, so in this problem I have a uniform cylinder of radius r rolling without slip on a flat surface. Okay, so let me first write this down. So uniform cylinder of radius r, okay, rolls without slipping on a flat surface, as you can very well see here. Okay, then there is a spring of stiffness K and a damping element of a damping constant C attached at the points A and B. Okay, so this is the first thing. Okay, the second thing is a spring of stiffness K and a damping element, damper of damping constant C are attached at points A and B respectively. Okay, their other ends are attached to the wall. Okay, their other ends are attached to a fixed wall. Okay, and the third thing is the mass moment of inertia of this disk is given to us as the following. So Ig of the disk is given to us as half m r square about the center of mass G. Okay, where m is the mass of the disk and capital R is the radius of the disk as well. Okay, for small displacements, okay, so obtain for small displacement from static equilibrium position, from the static equilibrium position, okay, obtain the equation of motion. Okay, the key word here is small displacements. Okay, so we're looking at incremental motion, and the aim is we got to obtain the equation of motion of this entire system. Okay, so first things first, we will look at what the kinematics of the problem are. Okay, so from the point of view of the solution, okay, I'm told that there is rolling without slip. Okay, so rolling without slip. Which means that the contact force is going to be the friction force between the cylinder or the disc and the ground, and it's not something that I'm interested in right now. Okay, but the basic idea is that at least the relative velocity at the point of contact is going to be zero and so on. Okay, so let me take the disc from above with all these labels on them. I'm hoping I can capture all of these labels without capturing too many of the other things. I think I should be successful. I'll see. Okay, so I'm going to do the kinematics first. Okay, so rolling without slip. Look at the kinematics first. Okay, so here is a disk. Okay, I did not capture the flat ground, but I want to copy that and paste that here, and I want to bring it down here so that that distance is r by 2 and r by 2, so on, and then I'll bring the ground as well, as you will see in a second. Okay, I'm going to copy that. That was not supposed to move. There was no earthquake there. Okay, so the ground comes right down here, and I can probably get rid of the rest of the ground. I don't need all of that. Okay, so cut that off. of course cut that off, and I can get rid of this too. Okay, so beautiful. So here is the situation. Okay, what are the things that we can do in this particular problem? We can write down the kinematic relationships. Okay, so since it is rolling without slip, I can say that the relative velocity at the contact surface between the ground and the disk is 0. Okay, so this says that velocity of C, of course, going back to my color, velocity of C slash D is equal to 0. I set up a coordinate frame. This is as usual. Okay, this is kinematics that we've done in the past, so there is not much to think about here. So this is the I direction, this is the J direction, and this is the K direction, and I can set up a tangential coordinate frame here. This is the tangential direction, which is at that point in time coincident with the I direction, and here is of course the normal direction, and maybe I can say that the tangential direction is coincident with I, and the normal direction is coincident with J at that instant. Okay, so first step is relative velocity is 0, which implies that velocity of C is equal to the velocity of D, and this is equal to 0 because the ground is fixed. Okay, by now this should be very routine procedure. Okay, then acceleration of C slash D in the tangential direction is 0, which implies that acceleration of C slash D in the direction that is the I direction is 0, because at that instant in time the tangential direction is the same as the I direction, which implies that acceleration of C in the I direction is equal to the acceleration of D in the I direction is equal to 0 because the ground is fixed. Okay, so which means that I can write the acceleration of C as having a 0 component in the I direction and some normal component in the J direction, which I am not very interested in at this point in time. Okay, and likewise velocity of C is going to be 0 as well. Okay, this is essentially 0I and 0J, and we also know that the disk cannot lift off of the ground. Okay, does not lose contact with the ground, which implies that the acceleration of the center of mass of the disk has to be in the I direction only. It could be positive or negative, we don't know. Okay, I'm going to assume that the disk is rolling in the clockwise direction, so I'm just going to give it a clockwise angular velocity and a clockwise angular acceleration. Okay, I'm going to call this omega of the disk, I guess omega D, and let me just call it as omega, and then let me call this as alpha. Okay, I'm going to assume both of them to be that way. Okay, so assume that omega is minus omega in the K, and alpha is minus alpha K. Okay, then all I have to do is write down the velocity expressions and so on. This is also regular stuff. We have done this in many problems before. I can say that velocity of point G is going to be velocity of point C plus omega of the disk crossed with R from C to G. Okay, if I do the substitutions, then I will end up getting velocity of G. Of course, velocity of C is 0, so I can cancel that off, and this is going to be minus omega in the K direction crossed with capital R in the J direction. K cross J is minus I. You can write your triad, and I'll write that down here. We may need to use that at some point. Okay, and if I look at my triad, then I end up getting velocity of G is R times omega in the I direction. This is the first result that I get. Okay, likewise, since I'm doing velocity analysis, let me do the following as well. Okay, let me look at the velocity of the other 2 points of interest for me as well. Okay, so I'm going to copy that, and I'm going to bring that down here. Okay, so if I look at the velocity of point B, look at this, or velocity of A. Okay, so velocity of A is velocity of C plus omega crossed with omega of the disk, if you want, I guess, crossed with the position vector from C to A. Okay, and velocity of C is of course 0, so which means that velocity of A is just going to be r by 2, and if you do the math, you'll get this to be r by 2 omega in the I direction. Okay, this is something that you obtain. And then likewise I can say that velocity of B is equal to velocity of C omega of the disk crossed with r b slash c. Okay, if I complete this out, a velocity of c is gone, write the position vector and so on, then you will end up getting velocity of b is equal to 2 times r times omega in the I direction. Okay, and so here is something that we can say. Why am I looking at the points B and the point A is because the spring and the dampers are attached at that point. Okay, so damper attached at the point A, at the point B, I'm sorry. Okay, so which means that the relative velocity, since one end of the damper is fixed, the relative velocity between the ends of the damper is essentially going to be VB. Okay, so damper is going to react to a relative velocity between its ends, which is why I'm interested in this velocity VB. Okay, so VB, I have it as 2 times r times omega in the I direction. Okay, then the spring is attached at the end A. Okay, this implies that since the spring is attached at A, the spring of course exerts a restoring force only to a displacement, relative deflection. Okay, so spring force exerts a force to a deflection between its ends. Okay, which is the difference between the displacement of its ends. Okay, and so here is the idea. We are going to say, okay, velocity of end A is going to be r by 2 times omega. Okay, and so and we also know one more thing, right? We also know that velocity of G is going to be r times omega, and this is in the I direction, this is also in the I direction. Before I go ahead and say anything about these two quantities, okay, and maybe I can write down the velocity of B as well, which is 2r times omega in the I direction. These are all things that we know. I want to look at the degrees of freedom and so on for the disk. Okay, so configuration coordinates, I need 3. Okay, okay, so 2 to locate, center of mass, G. Okay, and then 1 is required to know the angular position. Okay, so the 2 coordinates of the center of mass. Okay, so which means that my configuration coordinates will be x comma y and then theta, where x and y is the location of the center of mass at any time. Okay, this much we know from previous things that we have done on disks and so on. Okay, number of constraints is one constraint is that y is equal to r. Okay, so this is fixed. The second constraint is that rolling without slip. Okay, which means that the number of degrees of freedom is equal to the number of configuration coordinates minus the number of constraints is equal to 3 minus 2, which is equal to 1. Okay, and in this situation the degree of freedom can be taken to be theta, because x and theta are related to each other. Okay, so here is the idea. Since Vg is I want to write the G as a subscript, I'm sorry. Vg is r omega in the I direction, which means if I look at just the magnitude of the velocity, Vg is r times omega. Okay, and then I can say that omega is the same as theta dot, and alpha is theta double dot, okay, where theta is the angular displacement of the disk. Right, this is also stuff that we've done in the past, which implies that Vg is equal to r times theta dot. Likewise, I can write that Va, which was a point at the bottom, so this is going to be r by 2 times theta dot, and I can also write that Vb is 2r times theta dot, and I can say the following, okay, this is an important statement. Since we are assuming that the horizontal motions are small, okay, sorry about that, and of course Vg is x dot, okay, so we can also say that Vg is x dot I, if I write it as a vector, plus y dot j, but y dot j is a 0 because y is equal to r is equal to a constant, okay. So this essentially tells me that x dot is equal to r theta dot, okay, and since we are assuming small horizontal motions only, or small displacement of the disk, we can say that since x dot is equal to r theta dot, I can say that x is equal to r theta. Okay, this is obtained from here. Okay, so this is the connection. The connection between the two is coming from here. Okay, and likewise I can also say the following. Okay, Va is r by 2 theta dot, which means that xa. Okay, so this is essentially, if you want to call this as xg, you can call this as xg. Okay, so our xg is equal to x, and likewise xa is just going to be the integration of Va, and we are assuming small motions. Okay, so which means that this is just going to be r by 2 theta, and if needed we can say that xb is equal to 2 times r times theta. Okay, so this is the big deal here. Okay, so story so far from kinematics, Vg was r times omega in the I, or r theta dot in the I direction. Va was r by 2 theta dot in the I direction, and Vb was 2 times r times theta dot in the I direction. Okay, and theta is the degree of freedom. Okay, and due to small motion, we can say that x is equal to r theta, where x is the same as xg, which is the location of the center of mass, okay, with respect to an inertial observer. And then I'm going to have xa is going to be r by 2 theta, and if needed xb is 2 times r times theta. Okay, so this is the story so far, and I can also do the same thing with the acceleration expressions as well. I think I have my figure from before still around. Okay, beautiful. Okay, I can write the acceleration of the center of mass, so I can say that ag is going to be acceleration of c, alpha of the disk crossed with r g slash c minus omega square of the disk times r g slash c, plus those relative terms which kind of vanish because g and c are on the same body. Okay, the a relative and the Coriolis and all these things vanish, so I'm just getting rid of them. And so if I do the math, okay, so this is going to be agi 0I acn in the j direction minus theta double dot in the k crossed with r in the j minus theta dot square times r in the j. Okay, so which tells me that if I look at the I terms here, ag is going to be r times theta double dot. and that's something else that I would be adding on to the kinematics. Okay, so from the kinematics, for roll without slip, we end up having the following. Okay, we have velocity of g is r theta dot, so that x of g is r times theta, and then velocity of a is r by 2 theta dot, which means that for small motions, x of a, which is where the spring is attached, is going to be deflected by an amount r by 2 theta. Vb is 2r theta dot, which means that xb, if there was a spring attached, in this case there's a damper attached, it's going to feel the relative velocity, so vb is what I'm interested in. But in case there was something of that kind there, so this would be our 2r theta. Okay, and then I'm going to have ag is r times theta double dot. Okay, so this is the summary so far. Once we have all of these done, then all I have to do is just go on and look at the kinetics of the problem. Okay, so now let us look at the kinetics. I just want to write that properly. Sometimes my writing is pretty terrible. Okay, I hope you can still keep reading me as I keep continuing to write the way I'm writing. Alright, so in kinetics, all I'm going to do is draw the free body and the kinetic diagrams and so on. Okay, so here is the deal. Let me go back and bring my original picture. Okay, so here is the idea. I'm going to copy this and I'm going to bring this down here. Okay, and we gave the disk an angular displacement, right, which was theta. Okay, and the disk is probably set into motion by means of maybe initial conditions or so on. Okay, so that is a typical situation that's going to happen. So I'm going to draw the free body diagram of the damping element and so on. So here is what is going on. So I take the damping element. Because of the fact that it's connected to the point B, it's going to face a velocity at that particular point. Okay, so if you want, you can write it this way. So here, this is going to be from the static equilibrium position. This is going to be x dot of b, which is going to be vb, which was 2 times r times theta dot. Okay, and if I draw the damping force, then this damping element, because of the fact that I am using the following as the sign convention. Okay, so this is defined from the SEP, as you can see, when the spring is unstretched. So from the SEP, as I give it an angular displacement, if the angular displacement is in the direction shown, then the end of the damping element connected to the point B is going to be pulled, and the damping force FD is going to be given as C times 2r theta dot minus 0, because the other end is attached to the wall, so which means that FD is going to be 2r theta dot. Okay, likewise, if I look at the spring element, right, if I capture this guy here, I'm going to copy that and paste it down here. Okay, so if I look at the spring element, the end of the spring here, as you can see, from the static equilibrium position, that's connected to the wall, so there is nothing going on there. So this is the end that is going to get compressed, based upon the assumption that if I rotate the if I give initial conditions such that the cylinder is rotating in the manner shown, if the displacement is in the direction shown, then the end of the spring connected to the cylinder is going to get compressed. Okay, so this is going to be compressed by an amount xa, which we had written as r by 2 times theta. Okay, so I'm going to draw this as a force Fs pushing this way. Okay, and this is the force Fs. I'm sorry, this has to be in the other direction, the opposite direction. Okay, so this is Fs, and Fs is going to be k times r by 2 theta. Okay, so I have Fs is and I forgot to put the damping constant here. I'm sorry about that. I should have noticed it. Something was missing here, so I just caught it now. 2 times c times r times theta dot, and this is going to be k by 2 and r times theta. Okay, so if the direction of the angular displacement is in the positive sense, then the spring is going to get compressed. I want to make a note of this. Okay, so if the angular is in the direction of the sign convention shown, then it will get compressed. It will be in compression. Okay, which is quite evident to see here. Then all I have to do to complete the problem and wrap up and then call it a day is draw the free body diagram of the disk and kinetic diagram of the disk and move on with my life. Okay, so here is what I'm going to do. I'm going to take the disk. Take the disk with only a few of the things that are shown. I'm going to copy that and bring that down here. Two things I need to show. I don't need to show that. Let me actually draw it out and then I'll get rid of some of these things. So I'm going to get rid of that. I don't show that, and these guys are not very important for me, the normal directions and so on. So I'm going to cut that off, cut this off, and then I have a distance of r by 2 here. Okay, now I have alpha in the direction shown, which means that I have to draw Ig times alpha on the kinetic diagram. Okay, so this is the kinetic diagram. Okay, likewise I can get rid of all of these adornments on the kinetic diagram. I don't need any of these things. I don't need any of that either. I don't need this point because that point is not important for me in the kinetic diagram. I get rid of that as well, and I copy that and I bring that down here. Okay, and the direction of the acceleration of the center of mass is going to be in the I direction, so this is going to be m times Ag, or this is going to be m times r times theta double dot. Okay, and Ig alpha is the same as Ig times theta double dot. Okay, and we call this point as the point C, the point of contact C. What are the forces on the free body diagram? Okay, now we got to be careful. Okay, first of all, I have the weight of the body acting vertically down, so through the center of mass I have m times g. Okay, then I have the contact force at the point of contact. This is quite obvious. Okay, so this is the normal force. Okay, then the other forces I have are the friction forces. So the way the problem is noted, I mean, if I give my initial conditions to be in the positive coordinate sense, for example, if this is the positive sign convention, if my initial conditions are such that they are following the positive sign convention, then the force of the friction is going to be pointing to the right. Okay, otherwise it's going to be pointing to the left. So it depends on what my problem is going to be doing at that instant in time. Okay, so in this sense, my friction force, I'm going to be drawing it pointing to the left. Okay, so it does not really make a huge difference in that case. I'm thinking that, okay, this is traveling on to the right and so on, so this is F mu, but this is a static friction force because this is in a state of rolling without slip. Okay, so it makes no difference to us. Then what are the other forces? The other forces are, I'm going to have the force of the spring. Okay, so look at this end of the spring, as I'm marking, was connected to the point A, which means that there's going to be an equal and opposite force acting there. Okay, so this is going to be F suffix S. Then what else am I going to be having? I'm going to be having the damping element, okay, Fd, which was not that end, of course, I'm sorry, this end of the damping element was connected to the point B, which means that there's going to be an equal and opposite damping force at that point, which I'm going to call as F suffix D. Okay, and now you can see why the friction direction is pointing the way it is pointing. Okay, the friction direction is the one that will try to prevent the point C from slipping, and if I try to sum moments about the point C, I see that the movement of the point C, the contact point C, is planning to go to the right, which means the friction force has to be pointing to the left, which is the way it is drawn here. Okay, so this is the free body diagram. And that's about it for my free body diagram, and here is the kinetic diagram which we had drawn earlier, and Fd and Fs are known to us. Okay, Now if I have to drive the equation of motion or derive the equation of motion, then I don't need the friction force and a normal force, right? Who cares about that? Okay, so I'm going to just some moments about the contact point and then call it a day. Okay, so to find the equation of motion, sum of moments at the contact point on the free body diagram, this is going to be equal to sum of moments at the contact point on the kinetic diagram. Counterclockwise rotations are positive, so here are my rotations. From this sense, I'm going to have FD times the distance of 2r. Okay, so that's counterclockwise. Mg is not going to cause a moment. Fs times the distance of r by 2, counterclockwise as well. Okay, and that's about it here. And then what else do I have? I have minus Ig theta double dot, because I had assumed the angular acceleration to be clockwise, and then mg times r, but it's in a clockwise direction, so this is minus m ag times r. Okay, do the substitutions. Fd is 2 times c times r theta dot times the distance of 2r, and this is going to be k by 2 r theta times the distance of r by 2, and this is going to be half m r square theta double dot, and then this is going to be m times r theta double dot times the distance of r. Then we will start cancelling things and go on our merry way. Okay, so r goes off, this one goes off, that one goes off, all of these go off, there's an r here, there's an r there. Okay, then I'm going to start combining the terms, bring them onto the other side. Half m, and then m is 3 by 2, so I'm going to have 3 by 2 m theta double dot, and then this is k by 2 times 1 by 2, so that's going to be k by 4, and this is 2 times 2, which is going to be 4, so this is 4c theta dot plus k by 4 theta is equal to 0. Okay, so this is the equation of motion. Okay, then I'm going to write this in a standard form. Okay, I'm going to write it in the standard form by dividing through it by k by 4, and this is set into motion due to initial conditions. Okay, and because of the fact that there is a damping element, and these are initial conditions, I just want to mention that they don't look too good to me. That is, if somebody comes and then gives this disc a little bit of a tweak, what's going to happen? It is just going to keep rocking back and forth until it comes to rest. Why is it going to come to rest? Because I have a damping element there. The damping element acts as a parasitic dissipation of energy, and because of that, the motion of the disc cannot continue forever, obviously, right? Okay, so I bring the equation into the standard form, divide through, I get 3 by 2 m divided by k by 4 theta double dot. Okay, then this is going to be 4c divided by k by 4 theta dot plus theta is equal to 0. Then compare. With the standard form. What is the standard form? 1 by omega n square x double dot or theta double dot, it doesn't matter what you call it. Okay, this is 1 by omega n square theta double dot plus 2 times zeta by omega n theta dot plus theta is equal to 0. Okay, which obviously tells me that 1 by omega n square is going to be 3 by 2 m by k by 4. So this is 3m, okay, divided by 2k times 4, or this is going to be 6m by k. Okay, so that omega n square is k by 6m. Okay, I hope the math is right. Okay, yeah, it does look like it. Okay, or omega n is square root of k by 6m. Okay, then I can also say that, okay, hey, 2 times zeta divided by omega n is equal to 4c by k by 4. Okay, or if I do the substitutions and so on, so 2 times zeta divided by omega n, which is square root of k by 6m. This is going to be 4 times 4 is 16c by k. Okay, I can get rid of the factor of 2 and then make this as 8, which tells me that zeta is going to be the following. So this is going to be 8c, and then I'm going to have square root of k. I'm going to have a k and square root of 6m. The square root is gone, so which means that I'm going to have zeta as 8c by root of 6km. Okay, which means that the natural frequency is omega n, which is going to be k by 6m square root. Whole to the power 1 by 2, and then the zeta term is going to be 8c divided by square root of 6km. Okay, this is the damping ratio. And these are properties of the system. Okay, so they don't depend upon any of the forcing functions or the forces that are acting on the body. Whatever be the forces acting on the body, if there is a torque or if there is an applied force, it does not matter. These are system properties or system parameters. Okay, and so this is the basic idea of the problem. Okay, it's fairly straightforward. We made use of a lot of ideas that we had looked at when we were looking at rolling without slip, and if that is really understood well, then this problem does not pose any much of a difficulty. Okay, so once again, a very quick recap of what I have done here. So here is the problem. I have a disk. Okay, the disk is set into motion by means of initial conditions. Okay, so disk set into motion by means of initial conditions. Okay, initial conditions could be either an initial displacement or an initial velocity or both. It could be both, we don't know, and we really don't care at this point in time, unless and until you are solving the differential equation, which you will be doing in later courses like system dynamics and so on. Okay, so here I give this disk a little bit of a tweak, and then I let it go. It's going to keep oscillating, and what it's eventually going to do, it's just going to eventually stop oscillating, right, because of the damping element. I have a spring, I have a damper, everything is starting from the SEP position. Okay, and I say that okay, I'm going to set up a coordinate a sign convention. Okay, so this is the sign convention that I had adopted earlier. Okay, so this is going to be theta of t. If the disk is rotating in the following manner, where it follows the sense of the theta drawn, then it's considered positive. And if that is the case, then the spring is going to be compressed and the damping element is going to be stretched. Otherwise, the spring is going to be in tension, the damping element is going to be in compression if it follows the other direction. It does not mean that the disk is rotating this way. It means that if the disk rotates this way, then the displacement is given a positive sign. Okay, and in this case, we wanted to find the equation of motion, so we went through a lot of kinematics, found the velocity of the center of mass and the other points of interest, and then we also made use of the fact that since the horizontal motions are very small, we can relate the displacements at the points of interest to the degree of freedom. Okay, the degree of freedom being theta, as we had written down here. And then once we did the kinematics, we ended up with the following relations, as you can see here. Okay, so these were at the points of interest, which was the center of mass, the point A where the spring was attached, the point B where the damping element was attached, and of course the acceleration of the center of mass as well. Then we do the kinetics of the problem. We draw the free body diagram of the damping element and the spring, and it is quite evident that based upon the sign convention that is used, if the disk is rotated in the clockwise sense, the spring is going to be in compression. Okay, otherwise it's going to be in tension. And so if it is in compression, then this is a situation that looks like at some arbitrary point in time. Okay, does not mean that the disk is rotating this way. It just means that if the disk is rotating this way, the spring is in compression. I just want to make sure that everybody understands this. Okay, Then I write down the kinetic diagram and the free body diagram of the mass. On the kinetic diagram, your regular culprits, Ig theta double dot and m times Ag. On the free body diagram, spring force, damping force, gravity, direction of the friction force, think about how we got this, and then the normal force at the contact. I need the equation of motion, so I'm taking sum of moments at the contact point so that the friction force does not appear here. So here the normal force and the friction force act as constraint forces. Okay, this friction force is the static friction force. Okay, if you're rolling without slip, then the force of friction at the contact point is the static friction force. Okay, because the displacement of the contact point at that instant in time is negligible. Its velocity is 0. Okay, and for small motions, it's negligible at that point in time. Okay. Then I go through and obtain the equation of motion. I write it in the standard form. I compare it with the standard form that we typically have seen in the past. Okay, and we say that, okay, hey, this term here is going to be the same as that particular term. Likewise, I can say that this term here is the same as the term that I have written down here. Okay, and then once I have that, I have the properties of the system, which is the natural frequency and the damping ratio. All right, I hope you all enjoyed this problem. I hope all of you are staying safe as well. Take care of yourselves, and I hope you all have a very great and a happy Thanksgiving. Okay, take care. Bye bye.